the Volvo S60 has the camera and performs, yeah, it has a funny story. So the Volvo S60 has the camera looking forward and doing people detection, pedestrian detection. This is a very difficult task. If you Google pedestrian detection, you'll see tons of articles from leading researchers and universities, and you'll come to the conclusion that the problem is not that solved. And here you have Volvo launching a product which apparently works reasonably well to launch a product, which detects people, measures the distance to the person being detected, and provides a warning, and at the last moment also actuates the brakes. So it's an emergency braking with response to a imminent collision with a pedestrian. So based, and this is not the only example, there are other areas which are considered difficult problems like face detection, face recognition, and there are software today on Facebook, on iPhoto, that do a pretty good job on both detecting faces and recognizing faces, and those tasks are still considered difficult tasks when you look at it at the level of reading academic papers. So this is the conjecture that I'll be making, which opens the more theoretical part of my talk, is that let's make the following assumption, that single-class visual detection and recognition is possible within existing methodologies. That means if I have enough resources, enough human power, the state-of-the-art material that we have today in machine learning and computer vision, both the techniques for measuring information from images and machine learning techniques of performing classification are sufficient. Okay, this is a controversial statement. Many people who would not agree with me, but based on the kinds of stuff that I've shown in the previous slide and additional results that you see in industry, this statement is more or less can be defended.
Single class is no detection.
So one object. You train a computer program to detect only people. You train a computer program to detect only cars. You train a computer program to detect only chairs, and so forth. So single class, you specialize in this narrow domain of task. And my claim is that with the existing state-of-the-art techniques, with sufficient resources are resources that are not available to a professor in a university. Sufficient resources that are available to a commercial company that can hire, say, 50 algorithmic people and software people and so forth, and do the task. Okay, so with sufficient resources, a single-class system can be realized. This is the assumption that I'm making. So yeah, the faces, there's face detection and face recognition.
Photos you have like recognition.
Yeah,
like this is my father, and then it marks it.
Yeah, but I'm talking about now the detection. So in face recognition, the face detection is also a difficult task. Many papers from 15 years ago that the Viola-Jones was kind of a jump in attention of face detection. It's still a difficult task to do face detection. And face recognition is one level above it. So let's extend this to O of 1 classes. So if you have 3 classes, then replicate your resources. Train each class separately and replicate your resources. So if we take this as an agreement, what about 1,000 object classes? It's not realistic to take the resources that were used to a single object class and replicate this 1,000 times. Not realistic in computational resources, especially if you are considering a mobile platform where all the computations are done not on the cloud but done on a computer, on a single workstation or a single smartphone or a single microprocessor. So the challenge is, how do you go into detecting or recognizing a large number of classes? This, I claim, is beyond the state of the art that exists today. It means if you take a commercial entity and you give them how many resources that they want, to do 1,000 object classes at the same level that is being done today with single object class is beyond the reach of the state of the art. So this is where I'm focusing. I'm not saying that I solve the problem, but this is the thrust forward. Yes.
When you say enough resources, with sufficient resources, you include resources also enough, as much as needed, training data?
Training data,
so
people, manpower.
1,000 object classes will still be a problem. You need to have sufficient training data for that.
No, that's not the point. The point is computational resources.
Right.
So how much computation would be needed in order to detect instances of 1,000 object classes? So for example, the pedestrian detection code that is running on the Volvo takes about, say, half of the power that exists on my laptop. So half of an Intel Core Duo, 2 gigahertz Intel Core Duo would be sufficient to run the pedestrian detection code that's running on the Volvo S60. Now, replicate that 1,000 times, it becomes unpractical. So a linear growth in your computational resources is unrealistic. That means if you have X computational resources for a single object class, you'll need 2X resources for 2 object classes. This linear scalability is not realistic. One has to devise methodologies for sublinear scalability, for logarithmic growth, and this was the title of my talk. If we go back, the scalability of visual recognition. So fitting computational resources for the task. So this is where I want to hit. Part of the motivation of looking at this problem is a project that I initiated about almost a year ago to build a system for the visually impaired, to aid a visually impaired person, and one of the main thrust of this goal is to be able to recognize a large variety of objects. So for example, if we look at these examples, if you have a video stream to be able to identify the instances of a large selection of objects, you're talking about 100 different objects, both indoors and outdoors. Okay. So this is a motivator setting the context for looking at a system, a portable system that has the ability for detecting a very large vocabulary of objects. We go to the.
This was done in real time on what product?
So this is one moment. Okay. So this is being done in real time on a specialized microprocessor. So it's not a microprocessor that runs on a laptop. It's more powerful. But again, linear scalability, no matter what powerful microprocessor you use, is unpractical. So in narrowing the stage a bit further, when you look at the system ingredients, one ingredient which is very computer vision specific is what measurements you take from the image. And this is an open problem. It's an open issue. You take pixels, you take derivatives, you take histograms of gradients, you take self-similarity, you take a pixel, you look at the similarity to neighboring pixels, and then you make measurements. How do you represent the scale space? The pool of measurements, whatever you do, the pool of measurements is going to be very, very large. And it makes a lot of sense to take a large pool of measurements and then select only those that are relevant for your task. So I'm not going to talk much about this part. At the end of the experiment, I'm going to show one way of making measurements, but this is a big branch of the problem. I'm going to more focus on this part, which is more machine learning in general, the inference engine, linear, the co-occurrences of measurements, non-linearities in general, and in this context, what makes a multi-class problem qualitatively different from a two-class, and this is what I'm going to focus about. So I'm going to focus about linear. I'm going to show some material about nonlinear inference engine, but the focus is going to be on linear and this part of the issue. What is qualitatively different between a multi-class and a two-class when you are considering computational growth as a function of the number of classes? Okay, so it's very important to set this stage where my amount of resources is not infinite. I'm not running things on the cloud where I don't care how much time things will run. I want to run the program on a single or a standalone mobile platform. Therefore, the computational resources is a major issue in setting up such a problem. Okay, so let's set up the problem. We're talking about objects represented by a pool of features, a vector x which has d features. The mapping from the object to the features can be nonlinear. I will not get into it much, but one example is decision stumps. If we have v1 to vn are the elements are my features, we can set up thresholds theta 1 to theta m, and the feature vector is going to be a binary feature vector which measures whether a feature value is above the threshold or not, and there are different thresholds. This is called decision stumps, and this increases the size, the dimension of my feature vector. If I had n feature measurements, now I have n times m features. But so just as an example that one can have a non-linear mapping from your feature measurements to the vector of features which you want to represent in your classification engine. But let's put this aside. So the problem is that d, the dimension here can be very large, and n, the dimension of my original measurements, can also be very large as well. Typically, we're talking about the tens of thousands of measurements you can make from an image, and this is also a problem that we want to deal with. Now, what is my training set? Vectors x and labels y. We have m, my training set size is m, and y takes the labels 1 to k. So because we have a multi-class problem, and let's say we have k classes, so for each example x, I have a label which is a number between 1 to k. And let's say k could be 1,000 object classes. What is my design goal? I would like my computational resources to grow sublinearly, ideally to grow logarithmically with the number of classes k. Okay, and let's see how this thing can be set up. So what would be the classifier or the family of classifiers? The family of classifiers, and this is, I'm not saying anything new here, the family of classifiers would be parameterized by a matrix W who has k rows, k is the number of classes that I have, and has d columns, d is the number of feature measurements that I have, where d could be very, very large. Now how do I classify? I receive a vector x, I do the product W multiplied by x. Since W has k rows, I'll get a vector of size k. And I'll take the index of the maximal value of this vector. And that index would be my classification prediction. Okay, so this is how we will set up our classifier. Now note what we have here, that the column, we can look at the matrix W from the point of view of columns and from the point of view of rows. Let's consider both. If we look at W from the point of view of columns, the column Wi corresponds to a feature xi, because W multiplied by x is a linear combination of the columns of W, where the coefficients of the linear combinations are the entries of the vector x. So a column I of W corresponds to a feature I of x. Now if xi is shared among a subset of classes, then the corresponding entries of Wi will be high. So if you look at the distribution of the values of the column Wi, it will tell you how the feature I is shared among the different classes, which is one way to look at the matrix W. So what will be the goal here? Find W with few non-zero columns. Now let's see why this is a useful goal to make. Let's look at the alternative, the conventional way of looking at multi-class, and this will be a one versus all. The classifier will be exactly the same. You have a matrix W, everything here is exactly the same, but now let's look at this from the point of view of the rows of W. Each row of W is a separating hyperplane, doing a separation between a class and the rest of the world. So in this case, we'll take k different classifiers, the row of W. Let's do k different SDN classifiers. Each one will produce a vector which would correspond to a row of W. And those classifiers will classify between class 1 and all the rest, class 2 and all the rest, class 3 and all the rest, and so forth. This is called the one versus all paradigm. Now while we do this classification, if we want to do feature selection, it means that each row of W will be sparse, will have many zeros. Now what is the problem in this methodology is that the total number of features to be used can still be very large, because the sparsity of the rows of W's are not coordinated between the rows. So you can have a set of features used for classifying class 1 versus all the rest, another set of features classifying class 2 from all the rest, another set of features, and then so forth. So the growth in terms of the resources, the number of features that you'll need will still grow linearly. On the other hand, if you would enforce that the sparsity of W is structured, it's not that it's a sparse matrix. You would like many of the columns of W to be 0. It means you are forcing the system to look for features that are being shared among classes. Remember the previous point of view when we looked at the columns of W. We would like as few as possible columns of W to be non-zero. What this will force the system is to look for features that classify a subset of classes versus the rest. Not classify one class versus all, but classify a subset of classes versus all the rest. And the problem here is that there is an exponential number of subset of classes. Right? If we have k classes, there are 2 to the k subsets. Right? So clearly we are entering into the territory of NP-hard problems.
Okay? So it's not really shared by many classes, but I would like this is high information gain or something. To discriminate the classes.
Yeah, but you would like it to discriminate, but not one class versus all, but kind of to group classes together and discriminate between that group, between that subset, and all the rest. In that way, if it is possible, it could be that this particular data that you give me and the particular task that you give me, it's not possible to find such features. But if it is possible to find such features, those are the features I'll be interested in getting first, because that will give me a sublinear growth in terms of my resources, and resources are measured by the number of features that I collect from the system that are being used to do the classification. Okay. So
why are features the number of non-zero columns? Or
okay.
why are resources?
Okay,
just the number of non-zero elements in that.
Okay, so again, each feature corresponds to a column of W. So if you have only 5 non-zero columns of W, out of these features of X, you are using only 5 features, because all the rest are multiplied by 0 columns, are not being used. Right? Now, the amount of resources that you use here is determined only by the number of features that are being collected here. So if you are using only 5 features, you are collecting from the image only 5 measurements, and you are using that for detection. Right? So the amount of computational resources is directly related to the number of features that you are going to measure from the image and use for classification. And you would like that as the number of classes grow, the number of features that you add will grow sublinearly. That's a sublinear growth. And it makes sense, right? You don't need to be a computer scientist to understand that this is really what you want. Say you have seen 100 object classes. You have collected tons of features that discriminate among those 100 object classes. Now I'm giving you a new object class. It makes a lot of sense that the amount of features that you need to add would be very small. It could be that you don't need to add any features. The existing features that you have already measured would be good also to discriminate the 101 object class from the rest. Okay, so, but if we now formalize this, what we would like a W with few non-zero columns as possible. So now let's see how this is formalized. So here's the definition of what's called mixed norms, or of groups norms. So a mixed PR norm of a matrix W, you take the columns of W, you apply a P norm to each column. Now you get a vector, and then you apply an R norm to the vector. So this is called a mixed norm. So in particular, let's look at what would be the infinity zero mixed norm of matrix W. You are taking the L infinity norm of the column. So L infinity norm will count the number of non-zero entries. Okay? And then, so you're taking the L infinity norm of the columns, and you're simply counting how many of them are greater than 0. Okay, so this would be the L infinity zero mixed norm. So this would measure the number of non-zero columns of W. Okay, you can put here not only infinity, you can put here any norm that you like. The point here is the 0 that you have here. We're using infinity because it helps us in the analysis later. Okay?
It's a norm?
L0 simply the number of...
the mixed norm.
Yeah, it's a norm. So the problem we wish to solve, so now we're going to set up a loss function, but we're going to set up a standard loss function. It's called the logistic multiclass. I'll set it up for you in a moment. So we would like to find a W that minimizes the loss on all the training data, subject to we would like that we'll have at most t non-zero columns. It means the infinity zero mixed norm should be smaller or equal than t, where t is the number of non-zero columns that we would like to have. So this is a non-convex problem. It's an NP-hard problem, and we'd like to find an approximate solution to this problem. Now, the problem itself, if we look at the previous work in this area, so let's see how the previous work kind of converges into something similar to what I've stated here. So if we look at multi-class SVM, support vector machine, so L hat would be the multi-class Hinge loss. Again, I'll set it up for you in a few slides. And you'd like to find a W that minimizes the loss and also minimizes the Frobenius norm. Frobenius norm is simply the sum of squares of the matrix. So this may find a W that will do well on classifying, but W will not be sparse at all. So that there's nothing here to create sparsity in W. So this is not what we're interested in. If you look at another way of doing it, called lasso, the same multi-class, the Hinge loss, but now we would like the L1 norm of W to be small. So the L1 norm is a surrogate for the L0. Right? So L0 counts the number of non-zero entries in a vector. The L1 sums up the absolute values of the entries of the vector. So it's kind of a surrogate. If you have a low L1 norm, you assume you're going to have also a low L0 norm. But it's not the kind of sparsity we want, because if the L1 will successfully find a sparse solution, W will be simply sparse. But it's not what we are interested. We want sparsity to be structured. We would like the columns to be sparse. Okay, so this is not yet what we're looking for. So let's go further to more recent work. So we'll have the loss, but now we'll do infinity 1. So infinity 1 would be a surrogate to the infinity 0 that we are interested. So it will not count the number of non-zero columns, but it will do an L1 norm. So again, this is an approximation to an L0. And it has what's the advantage of looking at the problem in this way? That this problem is convex. So an L1 norm is convex. The loss function is convex. You have a convex problem. You have a convex problem. You can find the global optimum regardless of what algorithm you use. Right? It's guaranteed to find the global optimum. The problem here is that the fact that you are using a surrogate to the L0 does not guarantee that you are actually going to get a matrix W where you have sparsity of columns. Yeah.
From L1 now, you go to L0, solve the optimization problem with the convex problem, then go continuously.
Well, it's not clear that you'll get where you want to get, because you solve the L, and I'll show some examples where we solve this problem. You get absolutely no sparsity at all. So from absolutely no sparsity at all, if you're doing a graduated way of going from a convex problem to a non-convex problem, doesn't guarantee that you're going to get something meaningful at the end. So the way we are approaching it, that we're going to attempt to solve the original problem, even if it's a non-convex problem, and find a good local minima to it, and then show that actually what we have is theoretically accurate, and I'll show that in a moment. Okay? So this is just a setup of a way to achieve the goal that I was saying by convexifying the problem. And what we're saying here, we're not going to convexify the problem. The problem is find a matrix W with as small as possible number of non-zero columns. Let's try to attack this problem directly, okay, without convexifying it. So this is kind of the what are all these multi-class Hinge loss? Again, this is something that I'm not sure how many of you know about it, so I'll describe it. So multi-class Hinge loss. So this is our classifier, right? We have a matrix W multiplied by our input vector X. We get a vector of k entries. We take the index of the maximal entry of that vector. So what would be the empirical error on a training set S? Would be simply for each X we get Y hat, which is the estimation of the classifier. We simply count the number of errors. So that's the empirical loss. So normally what we would like is to minimize the empirical loss. The problem is that the empirical loss is not convex. So all the other losses is a way to convexify the non-convex empirical loss. Okay? So what is the Hinge loss? The multi-class Hinge loss is an extension of the two-class Hinge loss, and this was introduced by neuroscientists and Cody Kramer a few years ago. So this is the empirical loss. We're simply counting 1 or 0 whether the estimation corresponds to the true label. So this is smaller or equal than the same empirical loss plus a non-negative entry. Why is a non-negative entry? Because y hat is the maximal argument. So wx y hat is always larger than wx any other index. Right? So this is always non-negative. This is why we have here smaller or equal. Now wx x hat, we can replace this by maximizing over all y wx y. It's the same thing. Now if you take the maximum and put it outside, we're making this even larger. So we have here this inequality. And this is called the multi-class Hinge loss. In the next slide I'll show some picture of it. And this is convex. So we took a non-convex measure and we convexified it. And in the next slide you'll see why it is convex. And then let's call this LHWXY. Now let's look how it looks like. So this is the multi-class Hinge loss. Note that it could be greater than 0 even when the prediction is correct. Actually, the loss is 0 if the prediction is correct, and the margin, the difference between these two is greater or equal to 1. So what does that mean? This is the empirical loss. It's 1 or 0. The multi-class Hinge loss is here. It is 0 if the difference between the true label and the estimated label is greater or equal than 1. So what we have here, we convexified, this is the convex function, right? So we convexified the non-convex empirical loss. Okay, and this is called multi-class Hinge loss. So now what we're going to do, to go to what is called logistic multi-class Hinge, we're going to apply softmax. Right? So softmax is that if we take a function f that has values over x, and we take the e to the power of that function, and we take the sum and the log, it approaches the maximum of the function. Okay. So what we have here, we have a maximum. We're going to replace this by log of the sum over all the possible values, and then we take e to the power of the function. So this is called softmax, and we have this inequality from here to here. Why did we do that? Because we want to create a smooth loss function. If we saw previously, we have convexified the loss, but it's not smooth. I would like also to smooth it for reasons I'll describe in a moment. So here we did a softmax on the maximum. So now this is a smooth function that we can take derivatives of this function, and let's call this loss of w over xy. What is going to be our entire loss? The entire loss is going to be the sum over these losses for all the inputs from my trainings.
So you don't care about P,
No, this could be for any. Usually there is here a P, and this P
About the exponent.
Yeah, so there is a P. In practice you put a P, but that P you put it in a way that you play with it, basically, because it's for numerical reasons. Yeah, there is a P. In here, in this expression, P is equal to 1. But in practice you put a P there for numerical reasons. Right? Okay, so we have here where are we standing? This is the empirical loss over all the training set. This is the Hinge loss over the entire training set. It's convex but not smooth, and this is the logistic loss that we are going to work with. Okay. So we started with non-convex, moved to convex, and this is convex and smooth. Why do we want convexity? Convexity means that the subgradient provides a lower bound on L. Smoothness also provides an upper bound on L. So if I have a smooth function, the derivatives are meaningful in terms of doing a gradient descent. If it's non-smooth, the derivatives themselves are not yet meaningful for a gradient descent, they only give me a lower bound. So convexity and smoothness, at every step I have a lower and upper bound, and then I can move along the gradient. So what are we going to do now? So let's go back to the formula that we have here. We want to minimize the loss. That would be the logistic loss, and it's a smooth function. I can take derivatives. Subject to, I would like smallest number of columns. So what we're going to do now is the general greedy approach, which is what is behind ADA boost and all the boosting techniques. So we're going to update W one column at a time. So at every round we're going to search for a column of W that minimizes the loss the most, and then we're going to solve for that column of W, and then we're going to do what is called fully corrected. We're going to solve again for all the previous columns that we have found in previous rounds. So every round we have existing columns that we have already found. We're going to look for the column that reduces the loss the most. This is going to be something very simple. Once we have found that, the index of the column that we want to add, we solve for it and all the previous columns that we found previously, and that is going to be a convex problem. So the idea is that we would measure the gradient of the loss over a column of R, and that would be, we take a derivative of the loss with respect to an entry of W, and that's a closed form expression that we can compute. And then we define the gradient, the norm, we take the L1 norm of the gradient, which would be the sum of all these measurements over the entire column of W. And that would give me a number, and we would like to find a column that maximizes this number. Okay, so we go over all the possible columns, and there are many columns, right? If we have, say, 10,000 possible feature measurements, we're going to do this 10,000 times. For each column, which corresponds to a particular feature, we calculate the contribution of that entire column to the reduction of the loss. And we look for, this is why it's a greedy approach, and we look for the column that reduces the loss the most. We take that column, and then we solve for the entire matrix W only over those columns. So we start with W equal to 0. F would be the set of columns, or the set of features that we are selecting, and we do T rounds, where T is selected in advance. We compute for each label and for each example, we compute this measurement here, and then we look for a column out of all the dimension of my feature space. We look for a column that maximizes the gradient with respect to that particular column of W. Let's call it F. We add F to the set big F, which are the set of columns, and then we solve for W. We minimize L is convex, right? So we minimize L subject to only all the columns that are in F. So now it's a convex problem because L is convex, and this is called fully corrected. What we can do here is, so this is all very well, but in order to avoid overfitting, yes.
L is just the hinge loss, or?
Yeah, L is the soft max over the hinge loss, not the smooth function. This is why I can't take derivatives. Okay, so
how do you do admin? How do you do
so L is a convex function. So now I have a convex problem over only those columns that are in F. So say I did 5 rounds. So now I have 5 columns in W that I would like to solve for, and L over those 5 columns is the convex function. And you simply do gradient descent. It's a convex function. It's whenever it's convex, you can say it's solved. Okay, but we do gradient descent over a MATLAB function.
W is already in F.
We recompute it. So this is what's called fully corrected. So rather than doing every column that you add, you solve only for that column. We solve for that column and all the previous columns that we have again. So you are correcting small mistakes by solving again for all the parameters. Since this is convex and the number of columns that you are looking for is relatively small compared to the dimension D. Say D could be 10,000 and you're doing only 100 rounds, and K is a 100. So you have 10,000 parameters to solve. It's nothing for a computer program. When you're talking to millions and tens of millions, it's something to reckon, but 1,000 is very simple. So it would be, at every round you go over the entire set of features. So it will be P to the multiplied by D multiplied by K, because in order to, so it will be D, P, K. So that's ignoring the amount of time it takes you to solve this problem as at a fixed amount of time. Okay. So it's a very simple mechanism, but you can say several interesting theoretical things about it. I'll just make the statements without going into details. If you'd like, I can send you a paper describing this. The first is what is going to be the generalization guarantee. So what we want, we would like to bound this term here. It's the probability of making a mistake over my space of examples, not over the training set, over the space of examples. This is usually what you would like. What we have is the probability of being correct over the training set. So the question is, what is the connection between them? The connection between them is that there is another term here, and this term depends on the size of your training set, the number of rounds that you have done, the number of classes, and log of the dimension. So, for example, this term would be meaningless if it's above, say, 0.5. It doesn't say anything. It means that if your training set is too small, you can, and your D is very large and training set is very small, this term could say that you'll overfit. Okay? But it does tell you that if your training set is sufficiently large with respect to the size K, with respect to log of D, such that this term would be small, then you have a generalization guarantee.
You have to be careful about T.
Yeah, so you decide what T is going to be. Usually what you do, so you stop based on a testing set, right? You have a test set, you work on the training set, and you see how you progress on your test set, and you look at and you stop at the point where you're overfitting.
I thought that you were always going to converge eventually. Increasing T will actually always get you into
Increasing, yeah. So at some point, increasing T will get you to an overfit. That's clearly. So what you do in practice, you move one T at a time, and you look how you are doing on a test set. And at some point, you are overfitting, and that's where you stop. Now, what
another estimate?
Okay, what you do also, and I started to say it before, but I did not. Here, what we do in practice, we add a regularization term. It's a convex problem, but now you can add lambda on a, say, Frobenius norm of W. What would that do? By playing with the value of the regularization term lambda, you are kind of controlling the overfit. So by having a larger lambda, you can tolerate larger T's than necessary.
The bound could be enough for that.
The bound could be enough. So by playing with two, one is looking at performance on a test set while you're increasing T, and second, also playing with the regularization term lambda to control the overfit. Yeah. Select and the regularization term where for solving, in principle, theoretically, you don't need a regularization term.
Do you need to look at the test set to decide to run your algorithm?
No, you need to look at the test set in order to decide what the value of T is going to be.
So you need it.
Yeah. So, but this is standard practice when you train a classifier. You train a classifier by looking at the test set, and you're not blindly working on a training set, and then once you finish, you're looking at the test.
This method, if I have the resources to sample the whole solutions, what's the definition of test?
You have a training set. You take part of it as a test set, and you don't use it for training, and you see your performance on the test set in order to get a feeling whether you're overfitting or not. Again, this is standard practice in designing classifiers. In order to make a good classifier, you need lots of data. There's no way around it. The human brain can work with a very small number of examples, and this is something which could be nice to talk about. The way we, in computational methods work, we rely on having significant statistical representation of the problem. You need a large data set, and the bounds also tells you that you need a large data set. Where was that? You need a large data set. Now, as a standard practice, when you have a data set, you divide it part as test, and you use the test set not only at the end of the process, use it only during the process to fine-tune the point where you are going to overfit. You're always going to overfit. If you do too much, you're going to overfit.
The complexity of your class.
Yes.
How many? Just like the dimension of the dimension.
That's right. Yes. Exactly. Okay, now the next one, the next statement I think is more interesting and less intuitive. So doing a generalization bound, it's more the standard practice. The next one is the following: a matrix W, which has a very good loss. Say the loss is smaller than epsilon, and it's the number of non-zero columns is R. Okay. Then Sherwood will guaranteed will produce a W with at most double the loss and at most double the log of the number of features. So it means that if you are looking for a sparse solution, if there is a good sparse solution, this algorithm will find a sparse solution where the sparsity is, the log of the sparsity is at most double the optimal sparsity, and the loss is at most double the optimal loss.
But it's square now.
Yeah, so if you take a log of, then it's, so
Well,
it's
if it was exponential, it would be log.
yeah, we're looking at the logarithmic growth. Yeah, okay, so exactly what's happening here. So it's square the number of columns. Okay, again, we're looking at how is this going to grow logarithmically. Right? So R, the idea is that R grows logarithmically with D. So if D was a large number, we take the log of D to be more or less R, the Sherwood will find something that is twice, in terms of the logarithmic growth, at twice of that. But it's written here R squared, so it's not squared. So this is the statement. It also says that, another note here, is that if we're looking at W, which has bounded entries, then it means that the mixed zero norm is bounded by the infinity one norm, which also means that if you run your algorithm to solve the convex problem, infinity one, and find a good solution, then Sherwood will also find a good solution because of this inequality. So what this statement tells you is that although the algorithm is very simple, you can even say simplistic, as all greedy algorithms, there are certain interesting guarantees of this algorithm that we also find them in practice, and then I'll show you in a moment. Yes?
Maybe I misunderstood, but the sparsity, the matrix that you find is T. But this is the number of columns.
Yeah, but we have here also the loss, right? So
no, but
it is possible to find.
You say that, but you didn't say how. I mean, that you choose T with this.
So choosing your T, it's not that you beforehand choose T. You move with your T by seeing how you are reducing the loss and also looking at the overfit by looking at the test data. And at some point you stop because you know that if you are going to continue with more rounds,
you find the T that minimizes the error on the test set.
Minimizes the you're looking at how the error progresses on the test set.
So it just was what we call the SRM.
Yeah.
I'm confused about the fact that the smaller the value of epsilon is, the larger the number of non-zero columns your algorithm will find.
Well, if you allow to find many columns, if you are using all the features, you can reduce the loss. The reason of looking for a sparse solution is not because we want a better classifier. It's because we want a classifier that has a budget of resources.
The better W star is.
Now, let's say if there exists a W star that has non-zero columns, and this is the loss of this W star, we can guarantee that we will find a W that has at most twice the loss and the square of the number of columns.
Squared divided by epsilon, divided by the loss.
Yeah, divided by the loss. So it means if you want to reduce the loss, then you'll have to add more columns, which also makes sense. If you like to reduce the loss, one way to reduce the loss is to add more features, to add more columns. Let's look. This is the last theoretical slide, and then I'll go to some examples. So what I showed so far is a multi-class linear classifier, because at the end of the day, what we found was a matrix W, and we multiplied the matrix W with a vector with the input vector X. Right? So regardless of all the nice things that I said, this is a linear classifier, with all the limitations of what you can do with a linear classifier. Now, nonlinearities can be introduced in several ways. one is I mentioned at the beginning of the talk, and I'm not going to expand on it, is the way you prepare the data. You go from measurements, you do some nonlinear mapping of the measurements, like looking at decision stumps, and decision stumps can be integrated in this algorithm very, very simply. So this is one way to add nonlinearity. Another way to add nonlinearity is by using what is called super vector coding. So this would be a piecewise linear classifier. And how would this work? So what I'm describing here is what is known as super vector coding. So if we have a training set, we would like to find a function from the instance space x to the labeled space y, such that fx is approximately equal to y for all the points in my training set. Right? So this is the goal of classification. Now let's look at v1 to vq, the anchor points from S. So anchor x's from S. Say we have 1 million points in my training set. I define 1,000 of those points and I call them anchor points. So in support vector machines, those are support vectors. So now these are going to be anchor points. Now if we look at Vj, if we take a point x and we look at its nearest neighbor, say in L2 norm, we look at its nearest neighbor, and that nearest neighbor is the point Vj out of those V1 to Vq, then we can look at the first order Taylor expansion. So Fx can be approximated by the point Vj plus the gradient at Vj multiplied by the difference. And we know from Lifshitz continuity that the difference between f of x and f of vj is bounded by the norm, the L2 norm of x and vj. So the closer we are, the better the approximation. Okay? So we approximated f of x as first order Taylor expansion around vj, where vj is the nearest neighbor of x. Okay? Now note that we can write this as a linear product, a vector u dot product with x plus vj. What would be u? So u would be the gradient. So see the gradient is multiplied by x. And what would be bj? Bj would be f here, and then plus vj dot product with the gradient. Okay? So this here is a of x. Okay? So now we can plug these two together, u and bj. So we have here a vector dot product with a vector x and 1. So now we can look at a mapping of x to this zeros everywhere except x and 1 at the jth location. So each location here, so let's assume the dimension of x is d. So each zero here is dimension d. We have here d zeros, and here instead of this is the place j, this would be x and 1. And what we have here is a dot product between a vector w, which has all these components uj and bj, and the mapping P of x. Okay? And this is called super vector coding, because what we can do now, we can do SVM, we can train SVM on this dot to find optimal W. So
what's the dimension here?
So the dimension here would be q, the number of we have each here corresponds to one of these points. So it will be q multiplied by d plus 1. D would be the dimension of x. So each zero here is d plus 1 entries, all zeros. And this entry here is d plus 1 entries, but has x and 1.
So this is for 1j?
So this is for every point x. You look for its nearest neighbor. So this is a nonlinear.
For every point x,
you look for its nearest neighbor, and then you plug in that particular location. You plug x and 1.
So this will be
d plus 1 multiplied q. Exactly. It's a huge vector. It's a huge vector. So now, let's look more generally on this. More generally, you can do a soft. Rather than looking for the nearest neighbor, you can look at all the nearest neighbor in a certain radius. So f of x would be approximated by the sum of all the anchor points. You have here 1 or 0, depending on whether the distance between x and vj is above a radius rj. And then we have here the same thing what we had before. So now, the mapping theta of x would be the same dimension, but now you don't have zeros everywhere. You have x and 1 everywhere, multiplied by 0 and 1, depending on the nearest neighbor relationship between x and all the things.
Should it be normalized somehow with the number?
And then we divide this by n, by the number of. So what would be our classifier? So So if now we are looking for a matrix W multiplied by theta of x, right? So what would be the classifier? The classifier would be look for all the anchor points in a set I. So the share boost would be choosing anchor points. So look for all the anchor points in a set I, where we are doing a linear combination of what we have here multiplied by a block of W. So let's call the block of W Wj. Wj is multiplied by x and 1, and then it's multiplied here by a coefficient, a 0, 1 coefficient based on the radius. So what we have here, we have a nonlinear combination because of this term here. We have a nonlinear combination of linear classifiers, one classifier per anchor point. Okay, so the more anchor points you have, the more accurate you'll be. So you start with a very large pool of anchor points, and you let ShareBoost choose those anchor points. So it chooses these blocks, d plus 1 blocks, one at a time. Okay, so this will be a non-linear extension of the simple linear classifiers that I showed. And then there's also a kernel extension, which I'm not going into, which gives you co-occurrences of features and so forth. So the point I would like to make is that there's a simple engine here which can be extended to include the non-linearities that people discuss, like kernelization, and some new non-linearities like using supervectors as part of it. So let's go into some examples.
Well, what is again the scaling such a feature? It's really the way.
So here the point is not the scaling, it's the choosing of anchor points. So the idea is that as you have more classes, the number of anchor points that you'll need to add grows sublinearly. So each anchor point is a feature.
What determines how much sublinear is logarithmic?
Well, we can say it's only sublinear, not with anything. Depends on the data, depends on the problem. It could be a problem which there isn't a sublinear growth. There are no features that...
It depends on
the problem. Yes. The point we would like to make is that if there are features that can be shared, we would like to find them. That's the point. So let's go into two experiments that I have here. Now, in order to normally when somebody computer vision shows experiments, he shows experiments on images and then looks at state-of-the-art data sets. There's Pascal, there is Caltech 101 and so forth and so forth. I can tell you, well, I knew this for years, but actually last year there was a paper that actually made this in a more formal manner. All the data sets that are in computer vision are useless. Are really useless, because the amount of data that they have there is negligible to the needs of the classifier. Then showing results on these public data sets, it's nice to have a paper accepted, but it's really useless. And the reason I'm saying it now without getting heat is that last year there was a paper, very nice paper by Antonio Torralba and Efros Ryosha, actually making this claim more formal, going over the public data sets, and they had a nice methodology of how to show that the data set is useless.
Useless in the sense that it's not a good representative.
So it means that if you do well on one data set, let's say you would like to do pedestrian detection, and there are several public data sets of pedestrian detection, you would assume that if you do well on one data set, you'll be able to transfer your abilities on the other data sets, and this is completely not true. You are basically learning the idiosyncrasies of the data set and not learning the task that you wanted to learn, which is detect the people, detect the pedestrian.
We know it for a long time.
We know it for a long time. Yeah, we know it for a long time, but it was nice that people tried to make it formal. So what I'm going to show is something that has some meat into it. And one way is to look at, let's look at the MNIST data set. It's a data set of digits. There are handwritten digits. There are 60,000 examples in this data set. So 6,000 examples per digit. We have 10 digits from 0 to 9. And this data set has been extensively studied for the past 15 years. Many algorithms, and we know what is the state-of-the-art performance of those algorithms on the data set. And here's just an example of how these digits look like. So the input is a 28 by 28 matrix, and the digit is centralized in this 28 by 28 matrix, and it's a binary. As you can see, it's a binary.
What are the two numbers?
The number is classified, the predicted versus the correct. I'll get back to this slide in a moment. So if we look at what is the state of the art, first, if we do a straw man exercise, but just doing a nearest neighbor. So we have 60,000 examples. So I forgot to mention that there are 10,000 test examples. So usually you train your algorithm with 60,000 digits, and then you are tested on 10,000 digits. And the state of the art algorithms achieve performance which are below 1% error. That means below 1/100 errors on the test.
You allow injection.
What do you mean injection? No. You have to make a decision. You have 0 to 9 and make a decision.
What are human performances?
Well, I think that it achieves human performance, the state of the art. I'll show you the errors that it makes. So those are errors in actually writing the digits. It's more or less close to the state of the art. So if we do a naive strawman algorithm, simply take the nearest neighbors. Take that for every test example. Look among all the 60,000 examples that you have. Take the 3 nearest neighbors and look at the majority vote of the 3, or take k nearest neighbors and use that as the label. You see that the error rate would be 2.7%. So it tells you something about the difficulty of the task. Right? So it's not that difficult. You only make 270 mistakes out of 10,000 examples. Now, instead of doing a simple L2 nearest neighbor, there are algorithms that do a very complicated, what's called shape complex, very complicated match between the 2 images. Doing a nearest neighbor with that complicated match gives you 63 errors on the data set, but the computation time is horrendous. It's not something that you can do in practice. If you do a 9 polynomial SVM, 1 versus all, so you train 10 different SVMs. Each SVM is a kernel SVM with a 9-degree polynomial. The number of support vectors would be huge, above 150,000 support vectors.
How do you choose how to do the final specification?
So it's like what we did before. Each support vector gives you a number, and you choose the index of the maximal number. So all these 10 different support vectors would be rows of the matrix that has 10 rows. And the errors is 56 errors, but again, the number of the amount of computations would be large. The state of the art, a neural network with I forgot how many layers.
That's convolutional.
It's a convolutional net, has 35 mistakes, and 35 mistakes. This is a very recent work. But now let's look at the computation time. We are achieving 47 mistakes, which is more or less close to the state of the art. Where if we count the computation time that we have, it's almost 3 times less than leading, and you have 38 times less than an SVM, and so forth. Now, let's show you.
Time is largely a matter of implementation.
No, actually, with the convolutional neural net, basically are looking at all the connections, and each connection is a max multiply accumulate, so you can actually know what's the number of.
With some array processing, you can probably cut it.
Okay.
What is really interesting here is that neural networks are back into business.
Yeah, that's it. But
Sometimes it's not learning, it's after learning.
After learning, yeah, the online, yes. So let's see what are we doing here? How much time do I have? 5 minutes? 15. So first I need to explain. Okay, we take an image. What do we do with that image? What are the measurements? So there are many ways to go about it. What we did is not unstandard. So there's nothing really original in what we're doing here. We took patches of 7 by 7 patches from image. So an image is 28 by 28. So we have 60,000 images. We take all the possible 7 by 7 patches from the 60,000 images, and we cluster them, and we make 1,000 clusters. The centers of those clusters are our features, 7 by 7 patches out of the 60,000 images. Let's call these patches WF. So F goes from 1 to 1,000. Now, for each such patch, we would like to associate a mask. Well, a mask will say, where do we expect this patch to appear in an image of class K? One way to go about it is to select, to have a discrete set of masks and let the algorithm choose one of the masks. What we did, we fit a Gaussian for each 7 by 7. We fit a Gaussian of locations for each class separately, and that Gaussian was then we made a mask out of that Gaussian. So each patch, so this is one of those, so each patch corresponds to so this is the patch, corresponds to a expected location for each class separately. So it means that if we had 1,000 patches, we have now 10,000 possible features where a feature is a patch and a mask. So now, among those 10,000 features, we'd like Sherwood to choose a few hundreds of those features. So what will Sherwood choose? We'll choose a 7 by 7 patch and its corresponding mask. Okay, so a feature is it's a pair. So how do we create now a vector? We have an image. We go over all the possible 10,000. Right, so we have 1,000 patches and 10 masks per patch. So we have here 10,000 entries. Each entry here, what we convolve the image. The image is 28 by 28. We convolve the image with the 7 by 7 patch, and then we attenuate the result based on the mask. Now, since the mask is binary, it's not a full convolution. We only look at the dot product at the area where the mask is. Okay? And we take the maximum of it, and this will be a number. So we have here 10,000 numbers. Now, what Sherwood needs to choose is among those 10,000 numbers to choose those 100 or 200 numbers and their associated patches that gives you the best performance in terms of online performance. So the algorithm after T rounds, Sherwood will select templates, which are those WFI and GFICI, where FI is among those 1,000 patches and CI is among 1 to 10. So there'll be T pairs like this, and the test image I is converted to a feature vector X bar in dimension T, where T is 100, 200, it's a small dimension, where each entry here is the maximum convolution attenuated by the mask. And what is the classification? The W here, the number of columns of W is T, the number of rounds that we have made, the number of that's the number of columns, and the dimension of X bar is also T, as we said. And we use W multiplied by T, and we take the maximum index. Okay? So runtime, if T is equal to 305, this is what we have here. This is the number of multiplying accumulate operations, which comes to 1/3 of the multiply accumulate operations of the leading. So we are in terms of computation time, we're in the real ballpark of the best performing engine.
Can you show those selected templates?
Yeah, I'm going to show selected templates. So now we do experiments where if we take the 60,000 examples, we do 266 rounds. Why 266? Because afterwards it starts to overfit. And you can see here the train and the test. We have here, it converges around 0.71, so 71 mistakes on the test. Okay, this is train and this is test. This is number of rounds. Okay, this one. But now what we can do, and this is again standard in this literature, we can extend the training set by taking each example and creating, doing warpings, affine warpings, and creating additional examples for each original example. So starting from 60,000, we can generate many more examples by taking each example and doing affine warpings. If we do that, we have now a larger test set. Then misclassification error goes down to 0.47 with expanding training set. We added 5 images added per original image, so now we have 360,000 training examples. Again, this is standardly done in this.
How did the test set to be so much lower than the training?
No, the test set remains 10,000. You cannot.
The error is much lower.
Okay. The training is much more richer, right? You'd like also to enrich the test sets, but the test sets remain fixed.
That's why
yes,
no,
that's right. But notice also that with t equals 70, the error is already below 1%. Right? So you're actually starting to get state-of-the-art performance after 70 or more features. But now another experiment. Okay, and these are all the mistakes. So you have here 47 mistakes, and what you have here is the predicted versus the correct. And you can see that when you make a mistake, it's more or less a reasonable mistake. This was predicted as 3, actually it's 8. Right. This was predicted as 4, and it actually looks like 4, and the actual number is 9, and so forth. Okay, so it's really small. Well, yes, this is why the state of the art really stops at 35, because those 35 mistakes, when you look at them, now even a human could make those mistakes. Right? It's a labeling experiment. Yeah, but no, some of the mistakes are, let's say, here. It's a 7. It's not that you cannot improve here. Some of the mistakes you wonder why it made that mistake, like here, 8 and 7. Why did it say 8? Okay, now let's look at. Okay, if we look at the matrix W. So this is the matrix W, right? We have 10 rows because we have 10 classes, and the number of columns are the number of features. And if we look at feature number 11, the template expected 9, it has a high value on 9 and has a low value on 1. That means that this template is expected in digit 9 and not expected in the digit 1. Now let's look at another test set for a different kind of experiment. This is called char 74. There are 36 classes, so we have the digits and letters. So we have 26 letters and 10 digits, 36 classes. There are 1,000 training examples per class, so one cannot expect to get very, very high performance rate with such kind of a training set. And there are 3,000 test examples. And this is just an example of how these. So the variability is font variability and so forth. Now the point here is not to see what is the best result that we can achieve, but to compare the growth in the number of features with respect compared to a one versus all mechanism. So now, if we do the following, so we did 2 types of training. So one is to do a one versus all. One versus all with the same mechanism that we have. It will be simply a logistic loss, a 2-class logistic loss, and you are doing a feature selection on a 2-class logistic loss, which is exactly what we do if you limit it to 2 classes. Okay? And now you just simply count the number of features that you have accumulated when you want to do 10 separate one versus all logistic loss classifications. And then we compare that to what we get with the number of features with Sherwood as the number of classes grows. So we start with 5 classes, 10 classes, up to the 36 classes. We want to see how the number of features grow. But we also did 2 tests. One is when we want to achieve success rate of 0.92, and other one with a more modest success rate of 0.8. So let's look at the 0.92, the blue one. So you can see that when you do one versus all, we have here an increase of the number of features compared to share boost, which is more or less flat. So this is what I mentioned before, is sublinear growth. When we look at the more modest success rate, 0.8, you have also a more modest increase of the number of features. Again, it's much higher than the increased number of features of share boost, but it's lower than what you have here. And it makes sense that the more you are pushing your classifier to an extreme in terms of performance, the more you expect that it will take more and more features, and that features will grow linearly. But the point is that with the same success performance of 0.92, we have a sublinear growth. And this is the main point that I wanted to make at the beginning of the lecture, is that this is what we want to achieve. We want to achieve state-of-the-art performance, and this is what the previous example has shown, but with a sublinear growth of my computational resources. Because this is the big challenge if you want to build a system on a portable, on a standalone computer not running on the cloud, that will be able to handle thousands of object classes. You have to look into your computational resources, and this gives rise to the problem of how your computational resources grow with the number of classes. Yeah.
Why does the number of features go down in the green line?
It goes down. There are arrows here. There are arrows here, but it's not that from 50 maybe
What's so new in the sharing? Because you were in the algorithm, you were always adding to the set.
No, but you're looking at, no, this is the number of classes. These are different problems. Here you are training a problem of 20 classes and you see what are the number of features. Now you are training a new problem with 25 classes, right? So this is not that you are adding features, right? These are, this is one problem, second problem, third problem. Okay? They're not they're not cascaded. They're not cascaded, exactly. So anything can happen. Since you're also looking for a local maximum. Okay? I think that's
Questions? Hi. So you began with the next grand challenge in the study. But what's wrong with cloud? This is the next wave.
Many things can be done on a cloud, but many things you want them to run on a standalone computer. So let's start giving examples. The project that I'm looking at, this project of aiding the visually impaired, computer should be on you. You're not going for every, because you want to have a real-time performance. You have a video stream coming into your camera, and on the video stream you would like to detect objects and give information to the visually impaired.
I have cloud on my headphone.
No, sending an image to the cloud takes time. You're not sending videos to the cloud and processing the video and coming back. It will depend on connection and so forth. But let's look at existing applications. There are some very nice applications that don't work well, but it gives you an indication where things are going. There's an application called OMOBI. OMOBI, you take a picture of any object. There's an attempt to recognize what that object is. So I'm taking a picture of a chair. Supposed to know that's a chair, and then it will give me suggestions of where to buy chairs. Now, how does it work? They don't have enough computing power to run it on the smartphone, so they send the image to the cloud. On the cloud, they try to automatically identify the object. In most cases, they do not succeed, and then they go to the crowd. So they have a Chinese person somewhere looking at the image. Everyone who has an iPhone, I suggest you. It's called OMOBI. It's nice. That doesn't work, but the concept is nice. There's another application called Meal Snap. You take a picture of a plate of food, and it's supposed to recognize what it is and give you the calorie, the amount of calories in the food. So it does try to do the same thing. It sends the image to the cloud. In most cases, it doesn't succeed to recognize, and then it goes to the crowd. Somebody actually tells you it's chicken salad or something, and it comes to that. Take, for example, Google goggles. You take a picture of the Empire State Building. Google wants to know it's the Empire State Building in order to give you information. So you have here a many thousands of classes problem. And again, it sends to the cloud, and there they try to identify what it is. But when you talk to Google, they tell you that the limiting factor that prevents this application to really progress is the fact that the image is sent and it's not done real time on the smartphone. So this is just tip of the iceberg. It is important to be able to have your computations efficiently designed from a system point of view in order to do applications in computer vision. It's not everything to be done on the cloud.
Is there a good reason why not go the other way around? To start with the full matrix, optimize the specification, and then start taking columns out?
Well, first, finding the full matrix would be also unpractical. We're talking about tens and hundreds of thousands of features. But again, we're talking about a very, very large number of features. Now, if you do SVF, each row is done independently from the other rows. So you're really not taking into account this sharing of information. This sharing of information could get lost when you do those different K different problems of this.
That the performance of such an algorithm, or how really large it's running, less features there are lower, depending on the statistics of the class. And I consider to put some measure of how good this can, how well this can perform, just like small number of features.
Well,
in terms
very good question. I don't think that we have a good answer to it. So, you could give me a data set in which the growth in terms of the number of features would be linear. There's no logarithmic growth. There's no sublinear growth. That means there is no feature that separates a subset of classes from the rest. There are only features that separate single classes from the rest. So whatever I do, I will never find a sublinear growth which will give me state-of-the-art performance. Now, the question is whether I can know this in advance or not. This is something that I don't have a good answer to, but this is what we're looking into it, trying to know in advance from the statistics of the data what kind of growth can be expected.
I have a question. I was a bit confused. You started the experiment part by saying that all the data sets are useless. And then you showed us experiments on these data sets.
No, this is not computer vision data set. This is not computer vision. Computer vision is real images, not digits and so forth. So the computer vision data sets that exist today, the leading one is called Pascal DOC. It's a kind of a competition that every year gets enriched. There are 20 classes, challenging classes like people, chairs, cats, dogs, airplanes, bicycles, and so forth. But when you look at the number of examples you have per class, first it's very unbalanced. Among about 10,000 or 20,000 examples, half of them will be of people, and then you'll have 100 dogs. How do you expect to have a dog classifier if you have only 100 pictures? And the claim is that if you look at all the good performing algorithms, the differences between them are all statistical error. Nobody does a good job, and any algorithm that does a good job on Pascal DOC hasn't really learned those classes, because when you try the algorithm on different data sets, it's completely fail. Creating data sets is a challenge on its own. For example, in this ORCAM project, we are spending a lot of efforts in creating data sets. So the way you do it, it's like the mechanical Turk, but a bit more structured. There are groups where we're hiring a group in Sri Lanka, group of people. You send them data. They have actually people who are putting bounding boxes around the images. You give them tools to do that efficiently. You pay about $0.01 per bounding box, so that there's kind of a payment procedure, and then you create data sets in the millions. For example, but there's a manual, and then what you can do, you can take your classifier once it's mature and use that to get a preliminary classification, and then use a human just to say whether it's true or not true, and enrich your data set. For example, the pedestrian detection that I showed you on the Volvo, the training set is about 2 million examples. So what you can do with 100 examples, you can do nothing.
Any more questions? Let's thank our speaker again.
Yeah, thank you.
We're going to take a coffee break.